And the stream is started. Hello, everyone. New session of Virtual DDD, our first one this after this long summer. I'm your host today, Christina. I'm part of the organizer team, and our very famous and special guest is Barry, with for me totally new and interesting theory. And I'm happy to give you the mic.
Okay, I'll get started then. So tonight we're going to have a brief introduction to something called residuality theory. Hopefully you can all hear me. Yeah. So we'll get started on that. So if you haven't met me before, I run a small company called Black Tulip Technology, where we do research and teaching and some consulting. And I'm a PhD candidate in the area of complexity science and software engineering. And that's the work that we'll be talking about mostly tonight. I've had a previous life. I've worked at a large American company as chief architect, and also been globally responsible there for the development of the role of solution architect, of the solution architect. What does it mean to be a solution architect in this day and age? And the thing that we're going to talk about tonight is this paper, which was released earlier this year, Residuality Theory, Random Simulation and Attractor Networks, which it really isn't as scary or as technical as it sounds. It's actually just a number of very simple ideas that help us to place the work of the software architect into the context of a modern interpretation of complexity science. So we'll get started with the problem. What problem are we trying to solve? And the problem is, why is software architecture so difficult? Why does it hurt so much when we're trying to do these things? And the problem, in order to be able to discuss the problem, I need to first introduce a concept, and that concept is something called hyperliminal systems. And a system, a software system, which you see this little box here, is an innocent little thing. It's not particularly complex. In fact, it's very, very limited in what it can actually do. It only does what we tell it to do. And it's basically mathematics. And in my view, it's a deterministic system. We can make it do what we want it to do, and we can make it do the same thing repeatedly and continuously, and we can test it and guarantee that it works in a certain way. And so what we normally say is that a software system is an ordered system. It behaves in a reliable fashion. It can be made reliable. We understand how it works, and when something happens in the software system, it's very easy to figure out, why did that happen? What was it that happened? And so it's an ordered system, or if you're used to Cynefin, you would call it a complicated system. So there's no complexity in the actual software structure. There's probably going to be questions about that at the end. What we do with this innocent, structured, ordered software system is we take it and we place it into a disordered, unstructured system, which is a business environment, which exists in an economy, which exists, it exists in a market, it exists in an industry, it exists in a society and a political structure, which is very, very far from ordered. In fact, we don't actually know what's happening in that system. We don't know what's going to happen. We don't know the impact of our actions in that system. And it is indeed a complex system. And as architects, then we have two very, very specific things that we have to do all the time. The first thing is that we have to be here inside this ordered technical system, and we have to decide, we have to make decisions about structure. We have to decide, how is this thing going to work? And how should it work? How should we test it? How should we verify that it works? And all those systems engineering things that we do every day that we're actually quite good at. But apart from doing that with the ordered system, we've also got to jump outside of that ordered system and into the disordered system, into the business system, into the human system, the social systems that surround it. And we've got to figure out what's actually going on in here. What does the software system need to do? And what kind of challenges or what kind of assumptions have we made about the external system that are influencing the structure of the internal system, the software system? And so as architects, we jump around back and forth between these two. We're never really in one, we're never really in the other. We're constantly jumping around, and it can get very, very viewing and going through other people's architectures. I can say that this confusion is very, very common. Where are we? What is it that we're actually doing? And if you're working with software, if you're working with an ordered, structured thing, you need a completely different set of tools than if you're working in a human or a business or a political environment. A completely different set of models and ideas for understanding these things. And what we tend to do as software architects is that we tend to apply the wrong methods in the wrong place. And so we go into human systems and we start drawing lines and boxes and we say the human system works like that, when it absolutely does not work like that. And our representations of human systems tend to look like circuit boards, chipboards, or software diagrams. And that's not how human systems work. And so the challenge of being a software architect is that we have to be able to work with both of these. Not only that, but we have to know when we're working with the ordered system and when we're working with the disordered system. And liminality is a concept that means that you're not in one place or in the other, but you're in some kind of transition. And we are constantly transiting between these two things. And the name for that kind of system is a hyperliminal system. And it's very, very important for us to understand that what we do in software is hyperliminal. It's not a complicated system. It's not a complex system. It's something else in between, because the software, another example of a hyperliminal system is a car. So a car is a structured, ordered thing that can be tested. We can predict how it's going to behave. We can mass produce it. And the car gets to live in a complex environment, which is traffic. The difference between the software and the car is that you can't change the color of the car or the number of the seats while you're actually driving. And that's why software needs this definition of hyperliminality to understand what it is that we're actually working with. And this leads us to the problem, which we said we were going to define. And the problem I've described as the problem with X. And so we take this ordered, innocent, structured software thing that we've designed, and we place it into this disordered, unstructured business environment. And after a while, something will happen. This X will happen. Something will pop up. And something that pops up will be something that we didn't know about. We didn't understand that it was there. We didn't know that it was going to happen. And this is sort of standard run-of-the-mill thing. And lots of these X's will pop up because this business system, this human system, is so huge, so enormous, has so many agents, so many possible futures, that there's no way we could have known those things were going to be there. And what actually happens is that when these X's pop up in the environment, they begin to stress the software. They begin to stress the structural decisions that we made. And so we will have made a bunch of decisions about platform, about language, about the number of components, about the way those components interact with each other. And each one of these X's is a threat to our project and a pressure, a stressor on our architecture. And a lot of times when these X's pop up, we have to go back to the drawing board. We have to look at our architecture. We have to rip it all down and put it back together in a different way. And the way that we solve this problem, the way that we have traditionally solved this problem as architects, is simply to shrink the size of this complex bubble around our project. We make it smaller. We reduce the size of it. We reduce the noise. And we do that with standard tools like requirements engineering, risk management. We use things like patterns and strategies and value stream mapping, and we make everything much, much smaller. And then we work in this nice, much more comfortable, much more predictable smaller bubble, which is actually a construct that we invent. It has no connection to reality, but it makes it easier to act without landing in analysis paralysis. Inevitably, though, what happens is as soon as we put it into production, or sometimes before we get to the end of our first sprint, this red X will pop up, this thing that we hadn't designed for, this thing that we hadn't thought about, and it will cause issues. It will lead to us realizing that this structure that we built, the structure that we designed, isn't appropriate for the environment that it's acting in, because this X has happened and we have to go and rip it apart and put it back together. And sometimes that can be an incredibly expensive endeavor. And this is the problem with architecture. Architecture means that we have to, at some point, early in a project, commit to a structure. It doesn't matter whether you believe in architecture or you believe in big design up front. At some point in a project, you have to commit to a structure. And when you commit to that structure, you then build upon it, and you force that structure to live in an environment where you don't actually understand what's going to happen in the environment. So there's a question from Aman: is there a name for this red X stressor? No, we just call all of our stressors X. Anything that pops up and we don't know what it is a stressor. The red stressor is the one that's outside our comfortable little bubble, and there's many such stressors in any one particular environment. And so the problem we have then when you define it like this is that we have to design a structure for an environment, and we don't know what that environment is. We don't know what's going to happen in the future. We don't know what's in there. We don't know what way these things are going to interact with each other. We have no clue. But we still have to design a structure, and we have to commit to that structure, because if we don't commit to the structure, we can't build anything. And so essentially, software engineering is an impossible endeavor, or software architecture is an impossible endeavor. How do you design a structure when you don't know what that structure is actually going to have to do in its future? And we'll talk a little bit later on about how this actually, how this sometimes works. And so if this was the state of play, if this is the way that reality actually worked, there would only be one solution to this problem. And that solution would be the solution presented very often by agile software developers. You can't do anything about this. You can't plan up front. There's no point in committing to structure. And even if you do commit to structure, you have to accept that you're going to have to rip this thing down and put it back together again. And if that was the case in 100% of software projects, then we would have to say, well, the only way to develop software is to use this kind of agile way of thinking and say, we'll deal with stuff whenever it pops up because there's nothing else that we can do. The problem with that is that there's a whole bunch of talented architects across the whole world who continuously, across their entire careers, build systems that survive these X's. And that's really interesting. That means that there are people out there who somehow have figured out how to do this. And the problem is that they haven't told us how they're doing it. And that's, unfortunate. And so that's the thing that makes this really interesting. How do we solve for this? What are those architects doing? And so a lot of what I'm going to talk about this evening comes from work that I did at Microsoft, where we were trying to create more architects. We looked around and we looked at what was happening with cloud, and we looked at the way the world was moving, and we said, we need many more architects than what we have. And that caused me, then they called me over to Seattle and they said, look, here's your job, create more architects. And I said, well, what does that mean? What does it mean? How do I create more architects? And because the way we create architects in our industry is we take a senior developer, we walk them over to the edge of the cliff and we push them in. And then we come back after 5 years, and if they haven't drowned, we have an architect. And if they have drowned, then we take another senior developer and walk them over to the edge of the cliff. That's how we create architects. And so I asked them, what is it that you want me to create? And they said, well, just create more people who can do what you do. People who can create structures that survive these unknown X's. And that led me to do a lot of thinking and a lot of reflection, because I realized then that I don't actually know what I do. As an architect, I can't properly explain what I'm doing. Now I can go back and I can gather all of the tools and all of the ideas that I've learned under my career, requirements engineering and risk management and scenario planning and all of these things, TOGAF and all of this stuff. But I know in my heart of hearts that none of that actually works. And so you can teach junior architects that, and that's what we're continuing to do, but it won't help them become the kind of architect who consistently across their career delivers these apparently impossible solutions. And so this led to me then dissecting my own method, talking to senior architects around me, dissecting their methods, trying to figure out what is it that we actually do. And it became very, very apparent that those of us who were capable of delivering this kind of system couldn't actually describe what we were doing. And that's a phenomena that's described very well by Donald Shahn in the book, The Reflective Practitioner, if any of you have read that book, about how over a career we build up a set of instincts that we really can't explain, but we're correct a lot of the time. And so it turns out then that there's been quite a considerable bit of work done on figuring out what is this, how do we solve this problem with X, what is this X? And essentially what we're describing is a problem of uncertainty. And there's an entire field of study dedicated to uncertainty, and we call that field the complexity sciences. And the complexity sciences are quite difficult for software engineers because we don't know where to start. It's an absolutely huge field. There's an awful lot of stuff going on in there. Almost all of it is incredibly interesting. And almost all of it is entirely useless to software engineering. So if you want to start digging around in complexity science, there are thousands of books, there are thousands of ideas, all of which are kind of repetitive. And one of the things I've seen when people are introducing the subject of complexity science to software engineering is that software engineers are bewildered. There's a lot of big words, there's a lot of really cool concepts, but at the end of every session or every class that I've been a part of where you're teaching complexity to software engineers, the question comes up, how does this apply to software engineering? And it's really, really difficult, and no one's really jumped that gap yet to say, this is what you do when you don't know what's going on. This is how you use the complexity sciences to actually produce software architectures. And there's an awful lot of talk, but it mostly ends up in workshops and facilitation and not anything concrete. So what we have to do is make complexity science relevant to software engineering. And that is what residuality theory is about. So on a philosophical level, residuality theory makes some very, very simple claims about the nature of the reality that we live in. Firstly, there are systems, and they are kind of arbitrary. What is a system? It's a bunch of stuff connected to a bunch of other stuff. It's not really any more complicated than that. And here we see it's represented as a little network diagram with nodes and links, or nodes and edges. And the only thing that we can say about any complex system is that something is going to happen. We don't know what, how, why, where, or when this something is going to happen, but it's going to happen because these things aren't static. They're open. They have lots of connections to the outside world. Things keep changing. And when that something happens, the system will change in some way. It will be different. And you can see here that the system, something has happened and the system has lost its little yellow node here. It's disappeared. And so the system has changed. And we call this leftover part. Now, let me see if I can get this to work. For some reason, my Apple Pencil isn't working on Zoom tonight. This system here in the middle is our residue. It's the leftover of the system. And we then know that something else will happen. The system will change again. And the future of the system will be a function of that residue. That residue will remain. Something will happen. It will get new nodes. It might lose a few more nodes. But the future of that system will be a function of the residue. And that's all residuality theory is saying. And it says that we can't predict what these somethings are. We can't predict what's actually going to happen anything that we project into the future is probably wrong and based on a limited understanding of these complex systems. So the only thing that we can actually say, now the pencil's working, the only thing that we can actually say is that something will happen, the system will be reduced to a residue of itself, a bunch of leftovers, and something will happen in the future, and the future of the system will be a function of residue. And what we're saying is we can't predict anything, we can't control it, we don't know what's going to happen. The only thing that we as engineers have control over is the shape of the residue. So that little software thing in the middle that we design the structure over, we get to decide not how it does what it does, not how it produces a function, but how it falls apart. And that means that for a lot of software architects, we thought we were designing cars or we thought we were designing traffic systems, but essentially what we're doing as architects is designing crumple zones. And what we're actually doing here is deconstruction, not construction. It's not about building things. It's about understanding how things are going to fall apart, because in complex environments, that's all we have. That's all we can lean on. And if you get into the game of trying to predict what's going to happen in the future or trying to control these complex systems by constraining them or designing organizations, you're going to get into trouble very, very quickly because they cannot be controlled. And so understanding what can complexity do for software starts with understanding that if you take a complexicist, someone who's done research in the complexity sciences, then we have to describe software in a different way than we have been doing. Because when we shrink the bubble, we create models, and those models, and we create models and methods and frameworks, and all of these things actually obscure what it is that we're doing. And so we have to strip all that away and talk about what is software engineering from a complexity perspective. What is it? And I'm going to introduce two ideas from the complexity sciences that are really relevant to us as software engineers. The first one is random simulation. And this is a standard practice from the complexity sciences, and it answers the question of what can we do when we don't have all the details, we don't have all the inputs, we don't really understand the entire environment around us. And a really simple example of such a situation is I have a square, and the square is of side x. And inside the square, I have a circle. And the question that I want to answer is, what is the area of this circle? Now, if you've studied the mathematics even at a high school level, and you look at this picture, you'll realize that you're in trouble because your brain is telling you, I know this. There's a formula. It's pi r squared. That will give me the area of the circle. But you don't know what r is, and you don't have any point of reference. You can't figure out what r is. You can say that r is less than x. That's pretty much all you can say. And so a way to solve this problem is to randomly simulate the environment. So what we do is we get some darts, and we throw a dart at our shape. And the first dart hits the shape in the circle. And then we throw a second dart, and the second dart hits the shape outside the circle. And we can say, based on our simulation of points in the shape, that the area of the circle is x squared over 2, because half of the darts hit the square, half of the darts hit the circle, so it must be half of the area, roughly. So the area of the square is x squared, and we divide that by 2. And it turns out that if you do this a lot, and take a lot of points in here, then what you end up with is very, very accurate picture of the area of these circles. And you can actually tweak this a little bit to give very, very accurate estimates for pi. And this is a standard technique, and it's known as a Monte Carlo simulation, or fuzzy Monte Carlo simulation. And it involves not gathering the entire picture, not having access to all the possible variables, but randomly simulating an environment until you have enough information to be able to say something about it that's relatively concrete or correct. And if you think about a lot of the tools that we use as software engineers, things like requirements engineering, if you take a class in requirements engineering, they'll tell you about how to get the correct requirements, how to use this method, this framework. But the truth is that requirements engineering can never, ever be correct in a complex system. Same with risk management. You can take really advanced classes as an architect in risk management, and you can figure out the probability of this and the probability of that, and you can even learn to bluff using ideas from Bayesian statistics. But at the end of the day, you can't say what's going to happen in the system. You always have this incomplete picture. And every time you write down a requirement, every time you calculate a risk, every time you use a pattern, every time you run an estimate on a project, every time you build a value stream or describe a value stream, you're actually randomly simulating the environment. You're making statements about a future which you cannot know. And those random simulations are going to be full of errors. They're deeply, deeply flawed because we can't tell the future. It's philosophically impossible for a requirement specification to be correct. It's philosophically impossible for a risk management, a risk register to be correct. It's philosophically impossible for you to say what's architecturally significant and what isn't in a complex system. And so what we're doing all the time is random simulation. And there'll probably be questions about that because that usually offends people a little bit. But it's if you think about it in terms of a scientific perspective, I'm not sabotaging anyone's methodology or saying that these things are wrong. It's just the way it is. And so the second thing that's important to introduce from the complexity sciences is the concept of Kauffman networks. And Kauffman was a biologist and a complexicist who worked in the 1960s. And he was interested in how did life come to be? How did we get from a bunch of proteins and amino acids to iPhones? How did that actually happen? And he used a model to structure how basic things can interact to produce very, very complex things. And he called these complex Kauffman networks. And they are, another word for these things is random Boolean networks. So they're Boolean. Every agent, so here you see a bunch of nodes or agents in this network, and every node in this network has two possible values, 1 or 0. So it's a Boolean network. Every node in this network also has, if you can imagine, a little function inside it, and they all have different functions. And that function makes a random decision when it's executed and decides, am I 1 or a 0? Oh, flips a coin. So a really good way to think about these networks, to visualize them, is to think of them as light bulbs. And so what happens in this network is, let's say we have a little button down here that executes the network. The function runs on every single light bulb, and every light bulb decides, am I on or am I off? And then you'll get different patterns of light every time you press the button because it's random. And a system like this has 2 to the power of n possible states. And that's a pretty big requirements document, if you think about it. And so Kauffman ran this experiment with n equal to 100,000 nodes. They were virtual nodes. He didn't have 100,000 light bulbs. It was done on a computer. And that's 2 to the power of 100,000 is a greater number than the number of known atoms in the universe. So that's a huge number of possible states that this system could arrive in. Then he started doing something really interesting. He started linking the nodes together so that this node here, if we just pick this one, its function was dependent on input through this link from this node here. So this node would execute first, decide I'm a 1 or a 0, and then push its 1 or 0 down the link to that node, which would then take that as input to its function. Now, they didn't know what each other's functions were. They were just connected in some way. And he started to play around with this, adding different numbers of links, making it more or less interconnected. And he discovered that when you do this at a certain level, the number of states in the system fell to 317, which was kind of shocking. That's a huge fall. 2 to the power of 100,000 to 317 is an enormous change. And so simply by interconnecting the nodes in the system, he managed to make the number of possible states fall. And for him, when he first observed this, it seemed like every time he ran the simulation, every time he pressed the button, the system seemed to keep going back to states that it was in before. And that was very strange. And so we called these states attractors. And it seemed like the system wanted to be there. It seemed like it always returned there. It wanted to be there. And this is possibly the most fundamentally important result in the complexity sciences, at least according to me. And this brings us to something called an NKP analysis. And what we realize is that the number of attractors in a system is dependent on a number of things. The first thing is n, the number of nodes in the system. And so for this system that I've drawn here, n is equal to 12. And there's a good body of work following up Kauffman's work to show that as n increases, the number of attractors in the system increases. And that makes sense as well, logically. The next thing that's important is K, and K can represent two things. It can either represent the maximum number of links that one particular node has in this system, in which case here, if we look at this thing, then we'll say K is equal to 3. Or you can also calculate the average number of nodes in a system, which gives you a slightly different version of K. And the third thing, and what he noticed then was that as K increases, the disorder in the system increases. The number of attractors in the system increases as we increase K. And he also noticed that as you shrink K down towards roughly 2, then the system becomes ordered. Ordered in the sense that we can understand it, it's predictable, it has a very small number of attractors, and the paths it goes through to reach those attractors is generally similar. And so the third thing that he discovered was that if he introduced bias into the system, that we could take systems with a high level of K and a high level of N, and using that bias, we could make the system more stable, reduce the number of attractors that actually appeared in the system. And bias works like this. If we take this node here, when it executes, it has a choice. It can send a signal through this link or through this link. And if it sends a signal through this link, not 50% of the time, so it has a probability or a value p of 0.5, and 0.5 this way, then we say that that node has no bias when it executes. It's democratic. And if we change this, however, and we say, no, this is going to be 0.95 and this is 0.05, then this node has bias. It generally, most of the time, sends its signal in a particular direction. And what Kauffman discovered was that as you increase the bias of the nodes towards a particular course of action, you would get a more ordered, more structured system, even when K and N were high. And the reason that this is important to us as software engineers, if you strip away all the frameworks and models and patterns and everything that we've learned across the course of our careers, you can see that every software project, every software design that you've ever been a part of has been a balancing act between N, K, and P. That's what we do. So N is the number of components, K is the number of links, and P is something we introduce through contract, schema, policy, error management, having similar responses to error, making sure that a service or an object or a function responds in the same way, in a predictable way every single time. And the reason we do that is because we're introducing bias into our systems. The reason that service orientation and those 4 tenets are so important is because it's all about introducing bias. And as you introduce bias, you can allow K to rise, you can allow N to rise. And so most of the time, when we're designing software systems, we're looking for what is N, what is K, and how do I increase bias? And we've dressed that up in endless volumes of text and thinking and methods and frameworks. And we get together at conferences and argue about these things all the time. Which one's better, which one is more efficient, but essentially they're all the same. Everything we've ever done as software engineers is essentially a random simulation of the environment through requirements or through user stories or through talking or reading tea leaves, whatever it is we do, followed by an NKP analysis of pretty random prospective software architectures. And so from a complexity science perspective, from the perspective of a complexicist, this is what software engineering is. And this, again, this can bring up a lot of feelings in people, say, well, my work isn't random and I'm not just doing this and things like that. But from a complexity science perspective, this is what we do. Residuality theory then can be combined with these ideas, and it does two really important things. Firstly, we're going to make our simulations more random, and we'll talk about why that needs to be done. And we're going to make our NKP analysis more explicit, because everybody's doing it, but you probably never thought about it that way until I said this now, that this is what we've actually been doing all the time. And it kind of makes sense. This is what we do. So what have we learned from those previous slides? Where are we now? Well, it turns out that when we have this innocent little software structure, which we've kind of randomly decided what it's going to look like, and based on gut feeling, based on a little bit of experience that we've had, maybe based on some frameworks that we've learned, but mostly gut feeling, we come upon a software structure, and that's something that's backed up by research. It's mostly gut feeling, and we have this huge, enormous system that surrounds where our software is going to have to live. And the problem that we talked about, the problem with X, is that we don't know what's going to happen in this system. Anything could happen. We can't predict what's going to happen. We can't even map all the variables. There's no way to model this thing. It's so big and unwieldy and ugly that we can never get a grasp on it. It's impossible. It's beyond our science. And that's a standard kind of property of a complex system. The system is so big and so complex that any model of the system would become equally as big and complex, and we don't have room to store all the information. But it turns out, based on Kauffman's work, we can make one assumption that makes this much easier. We don't need to worry about this entire bubble. All we need to worry about are the number of attractors that this system is going to visit across its life cycle. That means that we don't have to know absolutely everything. So we don't have to know all 2 to the power of 100,000 possible states that every agent in the system can arrive at. We just have to know those root n, those 317 attractors. What are they? And it turns out that most of the time when we build software, we talk to business stakeholders, we focus in on one attractor, or one or just a couple of attractors, and we build systems that are far too narrow. And that's because our ability to simulate those systems is limited by the way we think about probability and by the power structures in our organizations. And so we tend to end up building architectures for happy path attractors, and nobody wants to talk about this unwieldy, unpredictable mess around it. So what we do is we use something called a residue in order to make architectural decisions in this situation. And what we do is we come up with a completely random X. Completely random. We just pull something out of the air that can happen in the business environment. And we say, when this X happens, what do we think is going to happen in our system? And the system will be pushed to a particular attractor. So X can be, let's say, what happens if a competitor drops their price? So then we say, well, what would actually happen if a competitor drops their price? A lot of architects are now going to say, we don't care, that's not our job. Okay, so anyone who thinks that, you're not an architect yet, okay, because architecture is about the interaction of the environment and the software. When a competitor drops their price, there's going to be a reaction. Your business environment is going to change. It's going to move to a new attractor, and that new attractor might be one where you buy your competitor. It might be one where you lower your prices, lower your margins, lower your IT budgets, and fire all those SAP consultants. It's going to be different. And then we have to say, in this attractor, does my architecture survive? Is it still there? And we say, no, it's not. These two components are now dead. They don't work anymore. The way they work as part of the system has been affected. They're not smart enough to survive in this new environment. We have to go and rip them apart, put things back together. But you could say that if we added this green component from the start, then the system would actually survive. It would survive moving to this attractor. And we call this the residue. This is what's left over of our system. And we change that residue to make sure that the system is more likely to survive in this attractor when this stressor happens. And we move that over to here, and we say, This is residue number 1. This is how we get our naive architecture, which is what we started with over here, our naive architecture to survive in this attractor. And we discover the attractor by randomly stressing the system. And then we take a second random stressor, which is going to push us probably to a different attractor. And we say that in this residue, we would need to add this orange component. And when we add that orange component, we put that over here and we call this residue number 2. And you've all probably experienced this. You've all probably had a system, someone's built the system, we put it into production, an X pops up, the system gets stressed, and someone looks at the system and says, well, this would have been easy to avoid if only we'd done this, or if only we'd split this component. And it's always easy to find these things. So we know it's possible. And we do the same thing with a different stressor, and we get a third architecture, and we call this our third residue. And what we do is what we end up with is a residual architecture. We have this original naive architecture, which is just a sketch, an idea of how we would solve the problem, and a whole bunch of residues that are similar, but sometimes very, very different. And what we then do is we integrate all of these residues into a coherent architecture, which gives us something completely different. And we'll see what actually happens. So it turns out for every residue that we design, there's usually more than one attractor that residue will survive in. And you'll discover that as you move through these kind of exercises. For every attractor, there's a huge number of possible stressors or events or happenings that can push the business or the social or the political system to that attractor. And what happens is, so Ricardo, I'll come back to that question at the end. What happened, or I'll come to that in about 2 pictures. What happens is that if we identify one out of these many X's, then we'll identify its tractor and we'll identify a residue that supports it. And this residue is actually something that will survive all of these X's because it supports all of these attractors. And so anything that pushes the business system into that attractor will be survived by this residue. And if you have that residue in your architecture, then you have a system that will survive all of these X's. Now, what happens when one of these other X's, let's say this one up here, suddenly happens in the system? Well, because you've already built a residue that survives in its attractor, your system will survive this X. And it will survive this X whether or not you as the architect or your business colleagues knew that this X was there. And what happens is we start to get architectures that look as if they're magical because they start surviving things that no one knew was there. And this is a very, very simple mathematical leverage. And it's caused by, if we go back to this diagram, it's caused by the fact that N in the software system is very, very small in comparison to N in the business or human system. And in fact, it's many, many orders of magnitude smaller. And so a simple random walk through a number of elements of N is enough to identify a huge number of the possible configurations in the small n. And that's what's happening. And so what we have is a mathematical leverage over reality that allows us to build systems that seemingly survive unknown, unpredictable sources of stress. Now, one of the problems that we suffer from, let me just have a look at Ricardo's question. So how does this differ from user story and edge cases? One of the problems that we have whenever we're working with complex systems is something called the curse of high dimensionality. The curse of high dimensionality means that a model or an understanding of a system, of a complex system, is so big, there's so many possibilities that our tiny human brains try to make everything smaller, exactly like that inner circle I drew on one of the first slides. We try to reduce everything, we try to model it down, we try to make it smaller. And the curse of high dimensionality means that we tend to focus on things that we believe have a high probability. And so whenever we're doing this thing with the circle and the square as software architects, we actually limit ourselves to a very small section of the circle that we think is going to be is going to happen. It has a high probability in our risk management. And then you'll get people who come along and say things like, you ain't going to need it, and keep it simple, stupid, don't think, just act, write code, don't think about these things. And what happens is that if you run this kind of simulation that I have on the screen here, you end up with a very small sample. Your random simulation samples around a very small percentage of the possible things that can happen. And what you end up with is you have a reduced number of attractors that you're building your system for. And as soon as you put that into production, it's going to crumble, it's going to fall as X's pop up all over the place. And it turns out this is an exceptionally difficult thing to teach to software engineers because we're trapped in this curse of high dimensionality. And we even have Yagni and KISS and all of these things to police ourselves and police each other and make sure that we never break out of this. And one of the things I teach then, and you might have seen me talking about this before, is one of the first X's that I make all of my students use in their projects is that giant fire-breathing lizards come up out of the sea and destroy the city that you're doing business in. And what's left of your architecture? What's your residue? Is it still going to work? And this is the sort of thing you can't talk to managers about because they get upset about it because it seems far-fetched. But the point of this is that the actual stressors that we come up with, it doesn't matter whether they're real or not. It doesn't matter whether they're actually going to happen. It doesn't matter if they have a high or a low probability. Probability is completely irrelevant. It matters if this stressor will uncover an attractor that we didn't know about before. And so if you do this thing, for example, with the lizards, you'll have built a system that will survive a bunch of X's for that destroyed city scenario. And the city doesn't even have to be completely destroyed. It can be an attractor that's similar. So you'll have built a system that will survive if there's a power cut. Okay? And that's something we may be about to experience here in Europe quite soon. It will survive if there's an invasion. It will survive if there's social unrest. It will survive if there's flooding. It will survive in heavy storms. It will survive as electricity problems. It will survive social unrest. It will survive recession because if your city's gone, no one's spending any money. And so what happens is that we see this pattern where using these stressors without recurse to probability actually builds a system that survives a lot of things that it shouldn't know about. And I have a much more concrete example of this. And so if we think about a system that's being built to manage the charging of electric cars, then we have a cloud-based system that's going to be used to decide whether or not you're able to plug in and charge your car at one of this company's fast charging stations. And the way it works, the naive architecture is that that you'll go in as a customer, you'll sign up on the internet, you'll put in your details, your credit card details and all of that stuff, and they'll send you a key fob home. And then you drive up to the forecourt, you drive up to the charger, you hold your key fob up against the charger, and once that's done, a little signal goes up to the cloud. It looks you up in its database and it checks, have you paid your subscription? And it says, have you paid for a subscription in this particular area? And then it allows you to charge or not. And so that's the happy path. That's the little red circle in the middle. That's the thing that got put into production, as usually happens in a lot of software projects. This is an example of the stressor analysis that could be done for such a project. And obviously this is a politically correct version. There's no lizards or anything in here because you don't want to scare management. And you can see the kind of things that might stress this system. And as if you're a very technical person, you might think, oh, these aren't anything to do with my job. But if you're going to get involved with architecture, you're going to have to step out into that big bubble and deal with things like what happens if there's a new car model introduced into the market? What impact does that have on our system? What impact does that have on the wider system? But there's three of these stressors that I want to focus on in particular. Number 3 here is a field login. What happens if I drive up in my, and this was quite a few years ago, so it's mostly Tesla. This was focused on, Tesla wasn't anything to do with this project. You drive up to the charger, you hold up your key fob, and nothing happens. So that's your stressor. What's the residue? The residue is you have a very angry, rich customer with a half ton of metal parked in front of your asset, and they won't move it, right? They might not have enough energy left in the car to go to the next charging station or to go home. They're not going anywhere. They're angry. They're on the phone. What do we do? And this turned out to actually be a huge problem, because these key fobs, they're sensitive to heat, they're sensitive to cold, they're sensitive to magnets, and they're sensitive to children chewing on them. They don't always work. So what do we do? And when looking at the residue for this, you have to admit there's nothing we can really do in terms of software to solve these key fobs. So we have to actually change the way the entire business process. And we use something called automated license plate recognition. And that's a camera that reads your license plate, uses a little bit of AI magic to figure out your license plate. And when we do that, we get rid of the key fob, and we can allow people to charge. No matter who they are, just charge your car and go away, because we don't want to have this problem of people standing there stranded. And what we'll do is, in certain jurisdictions, we can use your license plate to figure out who you are and send a letter to your house saying, you owe us this much money. And that makes it flow much easier. It's a standard edge case, so nothing special going on here. The next stressor that's important is stressor number 8, and that is damage to our chargers. Someone's going to drive into them. Someone's definitely going to drive into them. We have cars moving at slow speed. People are confused. They're looking around. They're going to hit them. Or we can have criminal damage, graffiti, that kind of thing. What do we do to solve that residue? What's the residue look like? The residue is we have forecourts that aren't working anymore because these things have become damaged over time. And we solve that with redundancy. Let's have a few more chargers than what we actually need on our forecourts, and with security cameras, so that if someone does drive into our chargers, we can say, hey, we know it was you. We have it on video, pay up. The next stressor that's interesting is stressor number 12. Stressor number 12, a customer abandons their car while it's plugged in to the charger, and they go and play golf, and they're gone for a whole day. And this turns out to be a massive problem, especially if the chargers are near a golf course or a city center and people want to go shopping. And here we start to see things a little bit differently. It turns out that there's a way to solve this problem, but it turns out the way to solve this problem is to use something from another residue, and that is ALPR, the automatic license plate recognition. So we can see when the car is there, and our camera can continue to take pictures, and we can build up a picture of how long has this car actually been here, and then we can invoice per minute. And it means that your first 25 minutes, which is what a fast charging session is meant to be, will cost the regular amount. The next 25 minutes will cost a lot more, and the next 25 minutes a lot more, and to the point where if you're there for several hours, it costs a lot of money. And at that point, this thing that was previously an irritation, a threat to our business, turns out to be something that gives us much, much more profit. It doesn't damage us at all. And all of these things are, standard business development. You might think that, well, we would get to this if we use scenario planning, something like that. What actually happens here, though, that's interesting, is when we look at stressor number 14. Stressor number 14 is something called icing. And icing is something that started to happen in the United States a couple of years ago. ICE stands for internal combustion engine. So an ICE vehicle is a fossil fuel driven vehicle. And icing was a habit that started happening in the United States, where people who owned ICE fossil fuel vehicles would park in front of electric car charging stations just to irritate the owners of electric cars, because they believed that owning an electric car was a political statement. And they didn't like that political statement, and so they wanted to irritate people. And this is one of those X's, one of those things that pops up that we can't predict, that the political situation would become more tense. We would have online misinformation campaigns, and people would start to hate each other a lot more. We didn't realize that was going to happen. We didn't realize how that was going to hit our business model. It wasn't in our requirements engineering. It wasn't in our risk management. We didn't even think about it. But here it is, and it's going to hurt us. And it turns out that a combination of the residues from 3, 12, and 8. So we have ALPR from 3. We've got your license plate. We have security cameras and redundancy. So we have you on film. You're sabotaging our business. That's a crime in some jurisdictions. And regardless, we're going to invoice you and send a bill home for on a sliding scale for the time that you're in front of the charger. So it turns out that this unpredictable, unknowable X, this icing, is perfectly protected by this architecture, which didn't know that it was there. And this is the pattern. This is the thing that first made me pay attention to the way that I was doing architecture. Because the way I was doing architecture was if you'd asked me 10 years ago, how do you do architecture? I would have said, I'm just really, really negative. I just sit down and I just think about things in a very negative way. And it turns out to be a very positive architecture. But this is a pattern we see all the time. If you arrive at your architecture through stress, instead of through requirements, instead of through risk management, instead of standard scenario planning, where you don't pay any attention to probability, we're a little bit wild in your definition of edge cases, then you build architectures that start to survive things that you can't see. And what will happen as you move through these stressor lists in any project is it'll start to become really, really, really difficult to stress the system. And once you get to that point, then we can go to the next step, which is called contagion analysis. Contagion analysis will help us to integrate all of these residues into a coherent architecture and will allow us to say, this is the structure. This is a structure that we can use, that we can depend upon, that we can trust in this environment. And that gets us very, very close to what these senior architects have been doing in their entire careers when they build systems that somehow magically seem to survive unknown sources of stress. And if you thought this was a particularly American problem, it's now spread to Europe. And this is a newspaper article from Munich, where people have associated the ownership of an electric car with vegetarianism and started to stuff the chargers full of mincemeat. And I don't care how good you think you are at risk management, nobody had someone's going to stuff mincemeat in our chargers on their risk register. It just doesn't. There's just things are going to happen. We don't know what they are. We're not going to be able to predict them. And we need a different way to protect against them. And so then we move on to contagion analysis. And contagion analysis is about how do we know that we have a decent decomposition? How do we push all of these residues together without making things too complex, too dangerous, too complicated, should I say, too dangerous, too involved? How do we avoid building systems that are even more shaky than they were before, without a great deal of cost? And one of the things that causes problems whenever we add more to an architecture is that we're obviously increasing M and we're increasing K. And that increases the number of attractors inside the system itself, which makes it more expensive to manage. And so what we tend to do is we design architectures that look like the one on the screen here, where we believe that we are isolating volatility in our architecture by encapsulating it. We deconnect our components from each other in a way that we believe will make the system easy to change. And inevitably, what happens, though, whenever we do this, and there are many different methods and different modes of thought that we can use to break a system down into a bunch of different components. But there's research by a professor in Canada called Paul Ralph, who shows that this process is more or less random. It's arbitrary. It's gut feeling. What happens then is that we have this thing and we think that we've isolated this architecture from particular types of change. Perhaps D is something that changes very often, so we isolate it as much as possible from the other components. And what will happen inevitably is that our stressor will pop up, our X will pop up, and it will hit one of our components. And in this case, it might hit C. And we've got to go in and change things and do things with C. And if we've done our architecture well, if we have good P, then that change should be isolated so it won't spread to B and D. But what we start to notice in reality is that stressors don't just hit single components. This stressor will hit C and it will also hit G, which up to this point we thought were decoupled from each other. They're not functionally coupled in any way. And in network science, if I have three nodes that are connected to each other, where the stressor is connected to C and the stressor is connected to G, that implies a relationship between C and G. What it means is that C and G are actually coupled. And that's why stressors are such a problem to us. These things that we don't know, we don't understand, when they pop up, they introduce coupling that was previously invisible. And we call this invisible coupling hyperliminal coupling, because the coupling isn't obvious in the software system itself. You need a stressor from the external environment to show you that these things are coupled. And because they're not coupled functionally, essentially what we're doing is we're discovering non-functional requirements. And discovering non-functional requirements is one of the major weaknesses of modern software architecture. We just aren't very good at it. It's very, very difficult. And it turns out that every project has many examples of this hyperliminal or invisible coupling. And it's like a spider web of invisible coupling between our systems, between our components. And this is what makes things difficult to manage, difficult to maintain, difficult to change. And has a very, very close relationship to the concept of non-functional requirements. And the way to integrate our residues and make sure that this doesn't happen is to run a really explicit NKP analysis. And we're going to use the concept of NK and P and stressors to find dependencies, interdependencies, and hyperliminal coupling. And so we use a tool, something called adjacency matrices, to figure out what the relationships between our prospective components are. And what we do, and this is something that they teach at MIT, this is what engineers at NASA and Boeing use to decide on the componentization of airplanes and spaceships, things like that. And what we do is we just create simple matrices where we show relationships between different components or different information flows or different functions. And we put a 0 where there's no relationship and a 1 where there is a relationship. And when we see this kind of pattern here, this little diagonal, this is an example of a process. This is quite a simple thing in this example. This kind of process, there's a relationship between the components, but it's very simple. We can give this to a junior architect. It shouldn't be any great problems here. What we need to look out for in these kind of matrices is this concept of mirroring. And if we draw this line down the middle and we see that this component is dependent on this component, and this component is also dependent on another component, we have interdependency. And interdependency, we all know what that means when we see it as software architects. We know this is bad. The reason it's bad is because you're doubling K. And as K goes up, the number of attractors go up, and the chance that your system will descend into chaos increases. And then we have incredibly complex scenarios where we have lots of this mirroring, lots and lots of interdependency. And this is a signal that either your business doesn't really understand what's happening yet. It's a very new environment. We're not entirely sure how all of this works. It can also be a sign that your developers are insane. And it can also be a sign that you're trying to compress too many things into one box, trying to make these components do too many things, and they're interrelated with too many other components. And so these are really simple heuristics that help us catch what's actually happening in the system. You can also have systems where the degree of interdependency is so high that the system in itself, K, is so high. And if you have low P in this kind of system, you start to get complete chaos in your system. And we've all been part of those projects. And that's, again, normally a sign that the business hasn't quite arrived at a mature state yet. It doesn't entirely know how all of these things work. And if you start to see these kind of things coming back at you as an architect, it's a signal that this requires a different set of skills, perhaps, than those earlier matrices that we looked at. And these adjacency matrices are a very simple way of understanding what's in here. What kind of subsystems, what's related to what, how mature how much has our random simulation actually given us. And if you start to see this kind of pattern here, you need to be suspicious. You need to think that my random simulation hasn't been random enough. I haven't gathered enough information as yet. And the final step that we use is something called an incidence matrix. And this is where all of these ideas come together to help us as architects make decisions about the boundaries of our systems. And What we do is we take a perspective architecture with a number of components or flows or functions, and we don't really have time to go into the details about that, but there's a number of different levels we can do this at. What we do is we take our perspective components and we run our stressors over them in a matrix. And if the stressor hits that component, we give it a 0. And if it doesn't hit the component, we give it a 0. If it hits the component, if it affects the component, if we have to change the component, it gets a 1. And this matrix gives us an absolute wealth of information about the architecture that we've presented. And again, the stressors themselves aren't really that important. It's the patterns. The stressors don't actually have to happen. They don't have to be real. And there's a bunch of things I can see here. Firstly, I can go here and I see that here we have a 5. Here I can see something's wrong. There's a lot of coupling. And if I see two components, say this one and this one, that both have a 1, then that's an example of this hyperliminal coupling. They're coupled to each other. And if I go back to my adjacency matrices and I see that they're not functionally coupled to each other in any way, then I've found a non-functional component. I can't describe it yet, but I know it's there. In this case, it's a server failure, so that non-functional component is really obviously an availability requirement. And we need to look at our architecture and say, is this the way we want to do this? Are we going to put all of these components on the same server? Is that a good thing for us? And then other things that we see are we see which components or flows are most susceptible to stress. And we can say things like, if this component is going to get hit all the time, we're going to need to take extra steps in our architecture to protect this component. Or can I refactor this component so that it's not getting hit all the time? You might have put too many eggs in one basket with this particular grouping of functions in this component. And this can be used to tease out all kinds of details about problems that exist in the business model. Another thing that happens is that if we look at any two particular components or 3 or 4 or 5 components that have the same pattern of response to stress, then we know that those components can actually live in the same building. They can live in the same place because they're going to get hit by the same stress routinely. And that's how we set boundaries with this methodology. It's not based on nouns and verbs or the relationship of one thing to another. Everything that has the same pattern or profile of response to stress gets to live inside the same boundary. That's how we make good crumple zones. And so there's a wealth of information that comes out of this final set of matrices that allow us to decide upon a structure. Then once we have that structure, then we have a component structure which should then survive a whole bunch of unknown stressors. And there's a way to show that we've actually achieved this. And so what we do is we start off with a naive architecture. And so someone comes in, the bottom orange row represents the totals, how many stressors hit this particular component. And so if that number's high, then we want to do something to get that down. Another interesting thing that I forgot to say is that if you take all of these numbers in the totals here and all of these totals here, add them together and divide them by the number of things that are in this, then that means that gives you a value of k. And if k is 2 or 3, then we're good. If k is 6, then this is going to hurt. And we need to rethink how we've done this kind of thing. If you have a 0 here, it means that you have a component that you haven't successfully been able to stress. And either that component isn't very important, you can't break it, or you haven't done enough work yet. It's very, very rare to say. This is just a sample from a particular matrix. It's very, very rare to find something that you can't stress because you can always pull the plug out. There's always a way to stress something. So what we do is we take this naive architecture, which is our first sort of sketch based on this limited story that our business stakeholders tell us about a system without really exploring it. And we gather a bunch of stressors and we use those stressors and we use our contagion analysis and we produce something called a residual architecture. And these two things will be quite different, even though they're doing the same functional thing most of the time. If we haven't changed our functions like we did in the example, because stress helps us find flaws in the business model, but they'll be different. And what we do is we have a second set of stressors, which we don't use to build this residual architecture. And we take these red stressors, which are unknown unknowns for both architectures. These are examples of X's. These are things that neither architecture was aware of. And we run the stressors over the naive architecture. And every time the naive architecture survives a particular source of stress, we give it a 1. And every time it fails, we give it a 0. And we add up all the 1s at the end, and we call that number X. And then we do the same thing with the residual architecture. We take these red stressors, we run them over the residual architecture. If it survives, we give it a 1. If it doesn't survive, we give it a 0. And then we go back through this list, and if they both have zeros, then we look at the residues and we say, which one has the better residue? Which one costs less to get us out of this hole? Which one is easier to change? And whichever one it is, we give that a 1. And at the end of this, then we can calculate something called the residual index. And the residual index is very simply y minus x divided by s. S is the total number of red stressors. And the result then is always going to be somewhere between minus 1 and 1, because y plus x is equal to s. And if that value is greater than 0, then you have empirical proof, a number that shows that you've done useful work. If it's greater than 0, then you've built an architecture that's more likely under experiment to survive unknown forms of stress. And empirically proving that you've done useful work it'll be the first time that architects have ever been able to do that. And so that's a huge step forward for us. Once you've done that, then we've got to go back to what you have an architecture, and you have an architecture that you believe in, which it can be a dangerous thing. And we go back to boring old systems engineering. We have to verify that this thing actually works, and then we can use, there's a lot of work being done around DevOps and SRE. I use techniques like failure mode effects analysis, the architecture trade-off and analysis method, which is scenario planning. It turns out scenario planning and stressor analysis are two completely different things, and that question's probably going to come now once we move over to questions. And all of these things, we're just constantly pulling it back to N, K, and P. And essentially then, what we've done is we have a much more scientific approach to understanding what is it that we do as architects, what does complexity mean to us as architects, and how can we actually do something useful based on an understanding of our world in terms of the complexity sciences. And one of the things that comes up is that some people are going to say, yeah, but I don't do any of this, and I still build good architectures. So how is that happening? And it can feel like when I'm giving these talks and when I'm talking about these things, it can feel like I'm being really harshly critical of a number of things like requirements engineering. And some people believe in requirements engineering. They believe in their methods and ideas that they've spent many years refining and getting better at. And some people believe in risk management, and some people believe very deeply that patterns are a good way to do architecture, and they get offended when I say this. And there's a whole bunch of enterprise architects who throw chairs at me when I say that capability mapping and process mapping are essentially lies. But what's actually happening when we do architecture is that we are producing slices of Swiss cheese. And for example, requirements engineering, as we've already discussed, is full of holes. It's incomplete. It's an absolutely terrible way to try and understand what's happening around us or what the future is going to look like, because you're asking people, what are your requirements for the future, when they don't know what the future is, you don't know what the future is, and they're not even in agreement with each other. And so you can think of requirements engineering as a slice of Swiss cheese. Okay, there's still something there that you can eat, but it's full of holes. And then we can take another slice of cheese, and that's risk management. And it's absolutely full of holes as well, because we can't put probabilities or impacts on things when we don't know what they are. We don't know when they're going to happen or why. It's mostly just storytelling. And it tends to form around that little red circle where we have a very limited view of what's actually happening in the system. As human beings, we're kind of helpless. And it turns out, though, that the reason good architects succeed is because we put layer upon layer upon layer of this Swiss cheese on top of itself. So we have requirements engineering, we have risk management, we use a pattern, we come up with estimates, we use backlogs, value mapping, capability mapping. We stack all of these things on top of each other. And what that does is eventually it means that we don't really have a straight path through all the holes. We cover for each other. And so when I do requirements engineering, and I do it really badly because that's the only way it can be done, it can't be perfect, it can't be right, and someone else, or perhaps even me myself, does risk management, then there will be risks and ideas that conflict with the requirements. And when I use patterns and I try to use a particular pattern to solve a problem because someone's used something similar to solve a similar problem somewhere else, that pattern will break when I expose it to the requirements or expose it to the risks. And what happens is we're creating conflict and tension between all of these models all the time. And architecture is not about figuring out the truth and then building a system that helps us manage the truth. Architecture is about producing conflict between all of these different modes of understanding. And so if you find a junior architect who isn't succeeding, it's because they just don't have enough slices of cheese. They're not producing enough conflict between the ideas that are circulating around the project. The more conflict that you produce, the better decisions you can make. And so residuality then, what it's doing is it's just coming along and it's adding layers and layers and layers and layers of sometimes quite ridiculous cheese, and it's causing conflict. And it causes conflict between all of our previously understood models of the system. And by constantly lifting this conflict, we discover more and more about the system, and we can build a system that at the end of the day appears to be magic because it survives things that it wasn't built to survive. And there is one slice of cheese that deserves special mention, and that is a non-functional requirement slice. And as we all know, because we've worked in this industry for a while, that is more holes than cheese. And this is a very, very serious problem for our industry. And these ideas, these methods that we've looked at tonight help us to uncover those things in a way that's much better than saying, tell me your non-functional requirements. We're copying someone else's non-functional requirements from a different project in a different context where they can't possibly be relevant. And so what we have here with this process of residual analysis is a brand new theory of software engineering, and at times very controversial theory of software engineering because it's new, and when something's new, you're automatically saying that the old stuff wasn't good enough. This upsets people a great deal. But what we have here are solid tools that actually solve problems, and it doesn't take very long to get up and running with these things. This stuff is properly researched. So one of the things I did a few years ago when I talked about this on stage and realized that people were interested in it was put it through put it through the academic, torture chamber, make sure that lots of people with lots of opinions got to beat it up all the time until it got stronger and stronger, sort of, and that's a bit meta. But the point is that this is not just coming from a place of experience, which and all architects who are experienced and who have delivered have a story to tell about how they get to a structure, how they get to a result. This is just one of those from me, and this is then researched and shown to work, and hopefully in a few months' time shown to be work in a way that is statistically significant. And that's a huge step forward for software engineering. Another thing is that this is compatible with all other methodologies. This is not asking you to give up on anything you do. It might ask you to be a little bit more skeptical about what you do right now and how much that contributes to your results as an architect. Because one of the things I find is that really, really good architects don't believe I'm a really good architect. They believe I use a really good methodology. But the truth is, it's not the methodology, it's you. You are the person who's delivering good architectures. The methodology is just the story your head is telling itself about how you get to those results. And so there's a considerable bit of material out there now. I usually say I've written 5 academic articles and 4 of them are rubbish. In a few months' time, I will say I've written 6 academic articles and 5 of them are rubbish. That's just the way it works. I'm doing this out loud and doing it transparently. I'm adding layers and layers and refining things over the years. I've even been published in a philosophy journal, much to the horror of my mathematics professor. So this is starting to form a fairly solid body of work, and the reactions I've had speaking at sort of large developer conferences over the last year are showing me that the interest in this is rising, that the ideas are refined enough now to be able to share on a larger scale, and people are coming back and reporting that we've done this and this actually works, which is really, really cool. And this paper then is the one that's been published most recently, which talks about a lot of the concepts that we've looked at tonight. And hopefully next year, after the publication of my PhD thesis, there'll be a book which should be a little bit lighter. And I'll take all the math and stats and put it in the back, and put a few funny stories in. So these are my contact details, and then I think we still have a bunch of time left, so we can move to questions. I can see a lot of them flashing past there in the thing. So I'll go through these and see which ones we have. So I already covered is there a name for the red X stressor? No, I just made it red, and to show you that reducing the size of the bubble is actually very, very dangerous. And I wanted to make that X different than all the other X's, and I wanted to scream danger, so I made it red. Then we have, how much do our stressors differ so much from user stories and edge cases? So user stories are generally based on about one perspective of the architecture, and you absolutely should gather user stories, and you absolutely should focus on the user's perspective, but you need to introduce conflict to that perspective. You can't just view things from a user's perspective. And edge cases, as we talked about, edge cases tend to be limited by what we believe is probable. And one of the things that I fight with all the time is getting developers and architects to write down their stressors, because they're scared, they're embarrassed to say something that other people don't believe in. And we don't realize how important, how psychologically influential this is, the pressure to be seen to be correct, to be seen to be reasonable, and to be seen to be able to predict the future means that nobody will ever say anything ridiculous. And if nobody ever says anything ridiculous or a little bit out there, then we stay inside that little red circle, and we continue to build architectures that are very susceptible to things which other people in hindsight are going to say, how did you never think of this? And so the example is the 2 engineers in Fukushima who reportedly sat at the back of the room whispering to each other about how the wall wasn't high enough. They didn't want to raise that because they didn't want to damage consensus. They didn't want to sound ridiculous. They didn't want to be pointed out as wrong by other people in the room. And so whenever we do the stressor analysis, there's 2 rules. One is no probability. You're never allowed to talk about probability ever. And as soon as you think of a stressor or someone mentions a stressor, you have to write it down and you have to use it. You're never allowed to dismiss it. You're never allowed to make that bubble smaller, no matter how ridiculous the stressor is. So it's very, very different than the concept of an edge case, because it doesn't have to have impact. It doesn't have to have a high probability, and we're never, ever allowed to sweep it under the rug. And this has implications for power structures as well, because that little red circle is generally decided upon by the most powerful people in the room. And generally our happy paths of the attractors that we believe in are an expression of what the most powerful people in the room believe is going to happen in the future. And just because they have power doesn't mean that they can predict the future any better than any of the rest of us. They're still limited by Western science, and they can't actually do it. And they won't take responsibility for it either. So the next question is from Amman. This one comes up all the time. How do we keep the complexity of such an architecture under control? Because it could very easily get out of hand. So there's two things there. One, architectures are never complex. Very, very rarely that we have a software architecture that's actually complex. That is, that N, K, and P are pushed to the point where the architecture does random things that we never understand every time we call it. Okay? Software is about a bunch of electrical signals going through a silicon chip. And as soon as we start moving those electrical signals through the silicon chip, we start restricting them and we start putting constraint on them, and more constraint and more constraint. And our software is just a bunch of layers of constraint. We're reducing the complexity of the system at every single step by making sure that it can do fewer things. And so, yes, one of the things that can happen if you try to solve everything is that n can get out of control. If you have so many residues and you're constantly adding new things, then you're going to make the system more susceptible to failure. And this is something that NASA discovered very early on during the Apollo missions, that you can make something 5 times redundant, but you've increased the probability of a component failure by 5. And we need to be careful about that kind of thing. And that's why the stressor analysis is immediately followed up by the contagion analysis, to make sure that we haven't actually introduced more problems than we've solved. And you'll see that very quickly because K rises very quickly. And so when you're working with your matrices and you say, well, can't we solve it this way? And you put a solution in, and what comes out of the matrix is that K gets higher, and that's an alarm bell. So we can actually catch those things. So every layer that I've talked about tonight, the stressor analysis, the randomness, the contagion analysis, and the matrices, the adjacency and the incidence matrices, and then following that up with tools like FME and ATAM, they're all like different safety nets. If you fall through one, the next one should catch you. If you fall through that as well, the next one will probably catch you. And they're all supporting each other and pushing you back up and causing conflict, because these ideas aren't correct either. Your picture of stress is bananas. It's got nothing to do with reality. So it will be wrong. But what I find is that the vast majority of changes that you make to a residue are very, very small. And the potential payback for those small changes is very, very high if such a stressor or such an attractor should occur. And most of the times it's about moving a function from one component to another, changing your component boundaries a little bit. Nobody actually cares about that. Right? No business person ever asks you about your software component boundaries. They don't even know what that means. Sometimes you'll come up with a stressor and you'll come up with an attractor and you'll realize, oof, we need to do something that costs a lot of money here. And at that point, you have to be good at, you have to know enough about architecture and business to realize that this isn't an architectural decision anymore. This is 2 architectural alternatives with 2 different costs, and that's a business decision. And then you have to be able to lift that up. So one of the things that I recommend is using things like the architecture trade-off analysis method from Carnegie Mellon, or a lightweight version of that, because it's a little bit waterfally and heavy, to make sure that you as an architect understand where the boundaries are between where do I make decisions and where does the business make decisions, and understanding when to let go and when to lift something up and say, look, there's more than one option here, but and we need you to make a business decision. One of the things that frustrates me is that I'll meet architects and they make business decisions, and they make business decisions based on an architectural view of the business. They say this costs too much, so we're not going to do it. This has more components, so we're not going to do it. I say, well, have you asked your business stakeholders or thought about what the implications of this decision are from a business perspective? Have you given them a chance to make a business decision? Or is this a little hidden surprise for the business for the day when X turns up? And you have to tell them that, no, actually, we can't do that because we optimized way too early for cost, which is something that we tend to do. Stressor checks are from a set that does not overlap with a set of user stories. Yes, if you have a set of user stories that you've developed and you have a set of requirements, then those are not X's. X's are things that your requirements and your user stories and your risk management have failed to capture. Everything that can happen in the environment, or that will happen in the environment that your system isn't designed for, is a potential X. And so if I'm doing my users, if I'm gathering user stories and I go around and I talk to a whole bunch of people, but I forget to talk to a particular demographic, and I have no information about how they feel about this, how it should work for them, then that becomes an X because we've missed it, because it's not there, because the system hasn't been prepared for it. So X is everything that we've missed. I talked about the numbers on the bottom orange row. So if the red ones are unknown unknowns, it's a good question. How do we know them to run the analysis? And we just keep them back. They're unknown. They're not obviously unknown unknowns because we know enough about them to write them down. So from our perspective, we know that they're there. We know that these stressors might actually happen. From the perspective of both the naive architecture and the residual architecture, from their perspective, they're unknown unknowns because they haven't been designed to cope with this kind of thing. So they're unknown unknowns from the perspective of the architecture. But obviously not unknown unknowns from us or the group that we're gathering our stressors from, because they've been able to talk about them. And there will always be unknown unknowns that we can't recognize, that we can't see, that we can never describe. And the way to cope with those is to gather enough residues to use that mathematical leverage so that we're solving as many invisible x's as we possibly can, even though we're not aware that we're doing that. Aman says that it sounds very much like biological systems evolve through stressors like disease, and what remains survives. That is very, very true. There are parallels with biological systems, but it's important to remember that an individual software system can't evolve. Evolution only happens at the species level, at the collective level. And so the evolution of software never happens in a single project. The evolution of software happens as an industry when we realize what fails and what dies and what lives. But yes, there are very obvious parallels with biological systems. And a friend of mine, Ricardo, gave a presentation last week, and he's a PhD in genetics. He talked about how biological systems have a lot of similarities with how we're now thinking about software, and how residuality connects into that. So there's definitely a connection there. And wouldn't you say that risk management somewhat works along the same lines of a stressor analysis and contagion analysis? No, they're completely different things. So one of the things we do as software engineers, we see a junior software engineer will make this mistake a lot, is that they will see two functions that are very similar to each other in terms of their inputs, their outputs, or their impact on the business. And they'll put both those functions in the same component and say they get to live together because they're functionally similar. And that's something that David Parnas wrote about in 1971 and said we shouldn't do this, and we still do it today. And that happens on the architectural level as well. So we see things like risk management or scenario analysis or business continuity planning, and we say, well, those things all look the same, and they look the same as stressor analysis, so therefore they must be the same, and we can do them all in one workshop. But they're actually very, very different things. So a stressor analysis is about identifying things that we haven't thought about yet and using that to raise questions about the structure of our software. And with the end result being that we have a better or more grounded set of decisions around software structure. Risk management is a business thing. It's about saying, if we're going to invest this much capital and we want to get this much capital back, what things can get in the way of doing that? It's a completely different set of considerations, even though there's a little bit of overlap in the subjects that we discuss. And so we are using the stressor analysis in order to arrive at an architectural structure. They are using risk management in order to do something called due diligence to prove that they've done their job as business people, because business is about risking capital in order to get a return. And so they're actually two very, very different things. When something comes up in a due diligence risk management, like if our device goes on fire and hurts people, what are we going to do? Then you're responsible for that on a business level, on a legal level. Whenever we're using stressors, we're just finding boundaries in our architecture in a way that's more thorough, more rigorous than running on the gut feeling that we have been up until now. And so all of these things, business continuity planning, risk management, stressor analysis, they look similar because we're thinking about things outside of what the system's actually meant to functionally do, but they're very, very different in terms of their aims, in terms of how they think about probability and how they think about impact. So in the stressor analysis, one of the rules is no probability, no impact. We don't talk about those things because we can't predict the future. On a business level, they have to talk about those things because they have to forecast and they have to be aware of these things. And they don't have to be right. They just have to show that we've done our due diligence. We have been good corporate citizens, and we have been good custodians of our shareholders' money. It's a completely different thing than asking where are the boundaries in my software. Unfortunately, we've let that boil together so much that we can't tell the difference anymore. And so risk management, from my perspective as a software architecture, from a business stakeholders perspective, as a manager of capital, from a project manager stakeholder perspective, as a person who has to deliver X on the 23rd of February, and from a shareholder's perspective, they are all completely different things. And the tools just won't work across all of those. You can't have one single tool that works across all of those perspectives. It's an incredibly dangerous way to think about and talk about risk. And then Dave, I say in theory, yes. In reality, requirements management has, okay. I'm not sure if that question is a response to.
At the end, yeah, we can go to Aman's next question.
Aman's next question.
Have
you also been applying this approach in real world systems? I'm trying to gauge what the uptake in the real world. Put it another way, have you had resistance trying to apply this approach? And what's the main argument against it? So let's go back 8 years. There was some resistance, and most of that resistance was coming from people who felt deeply offended by what I was saying, people who had got very specialized in requirements engineering or risk management or using a particular pattern or process or framework. And so one of the ways that I tried to make my working day more entertaining was to just provoke enterprise architects and say, well, actually, none of this works, right? TOGAF doesn't actually work. And that was how I started the conversation. And that led to some resistance. I have to say that for the students who I have taught these methods to in detail, there is no resistance. No one, once people sit down and work through an example based on their real life projects, and they start to see the results coming out of this, there is absolutely no resistance. People say, well, this is working. Okay? I can see this working. I can see how this approach is making my architecture better. The resistance is almost zero. Resistance tends to come from people who have a different set of beliefs. People who really believe in requirements engineering or really believe that I'm fully baked. As an architect, I know everything. I don't need your theories. I don't need new ideas. I don't need to think about things. I can do everything already. And to those people, I say, well, go. I don't care. If you are building everything you need to build and delivering everything you need to deliver, then that's fine. But I think if they look deeper at it, they'd see that they're actually doing these things. The main argument against this, I think you've already made, Aman, is this is going to cost too much. But with a little bit of experience, we realize that this doesn't cost anything. Okay? This is thinking, and there's a small cost in whiteboard ink, but that's not a great amount of money in the scheme of things, longer scheme of things. The cost of this, in reality, is that you as an architect have to do a little bit more thinking at the start of a project. And if you're an architect, you know that there's 2 weeks of air at the start of a project where you sit in meaningless work, meaningless meetings, and you can use that time to think through these problems. I've never really experienced any resistance to doing this as an architect in the real world. And one of the things I teach in the course is how to do this, how to use these methods without people necessarily needing to know what you're doing. None of your business stakeholders, none of your managers understands or knows what domain-driven design is. And yet we're all using things like domain-driven design in our projects, and we're not telling them about it. It's none of their business. We don't want them involved in those kind of details. So you don't need to tell them that you're doing this. You don't need to ask for permission to do this, and so you don't get any resistance from them. And so the way that they see this, the way that this is surfaced to them, is that I come in and I say, hello, business stakeholder or project manager or whoever, what keeps you up at night? What are you afraid of? What can go wrong here? What's happening in our competitors? What's going wrong for them? And they love these kind of conversations. And they say, this is great. I love talking to you because the last person who was in here just kept asking for something called non-functional requirement. I have no idea what they were talking about. This is a much better conversation which I can actually answer. And in terms of resistance as well, when you use these ideas, you really don't have to give anything up. You don't have to stop doing things the way you're doing. It's not oppositional to anything that you're doing as a software architect today. If you're a software architect who successfully delivers, then you're doing things right. This is just another prism, another way of looking at things, another way of explaining and articulating what we do. And the biggest benefit, just to flip this around, the biggest benefit that people are seeing from these kind of ideas is that if I take a whole team of architects at a particular company and I teach them all these ideas, they very quickly get a common way of describing what's happening, a common way of describing where it hurts, and a common way of dealing with problems. And that's been the biggest advantage. And whenever you have that kind of thing in your back pocket, then there was absolutely no resistance to these kind of ideas. So this is a really good question. What kind of system would you apply this kind of methodology to? And if you think back to something like Contagion, which I assume most of you are familiar with at this stage, if you try to do this on a very simple project, which is well understood, which has best practices, which has been done many times before, it won't work because you won't find enough stressors, and you'll try to stress it, and you'll realize the solutions that are out there today, the patterns that are out there today, they already solve this. You can't improve this thing by stressing it. And so those kind of simple systems, we shouldn't really use these ideas on. And so what I would say is very large scale systems, enterprise systems especially, that's where I come from. I've used these ideas at startups. Anything where there's a great deal of uncertainty about the business model, this kind of thinking helps a lot. So anytime any large enterprise or startup is doing something that's new in its market, these ideas work really, really well and create really good discussions. I haven't really seen any system where we shouldn't use this. And generally, when we have a really simple system, I like to run these ideas anyway, because one of the things we're terrible at is understanding when a system is simple and when it's complex. And running these ideas helps you get to an answer very, very quickly. And as I said, these ideas, these methodologies are cheap. This doesn't cost a great deal. The only cost is in mental effort. Where you have to read and understand and get a grasp on these ideas. And then Ricardo has a comment here. Conceptualization and abstraction to not be overwhelmed by the complexity of the non-ordered environment, because it lessens this fact can, in a residual architecture, work against this because it lessens our ability to identify stressors. Yes. So there's a cliche that says that all problems in computer science can be solved by adding another layer of abstraction. And residues are essentially a layer of mental abstraction. And what they allow, and so one of the things I thought about and discovered when I talked to other senior architects and thought about my own practice when I was trying to figure out how do I teach architects to be architects, one of the things I discovered was that the very senior architects were able to have many, many ideas in their head at the same time. And they were able to think about all of these different X's and all of these different residues, even though they didn't call it that, and attractors. So they were able to have all of that in their head. And they were able to realize that if I make a decision over here, it's going to ripple around, it's going to end up over here. And not everyone has that ability. And so the residual analysis, where we write down all our residues, and the matrices allow us to put all of that onto paper, take a deep breath, think about something new, and then look back at the paper and see where does it ripple, where does it capture. And it actually makes it easier to be an architect, because without these tools, being an architect means carrying all of these variables, all of these ideas around in your head. And it's really, really easy to forget. And so this captures all of these things. And it also makes it easier. It means that temptation to reduce, to compress the model, to shave things off, to say you ain't going to need it, or let's keep this simple, or let's not talk about things that might not happen. It becomes easier, and it becomes, in my experience, and as I see when I teach this, it becomes much more playful. Architecture done this way is lizards are so much more fun than TOGAF, and it becomes so much more fun to work like this. So the next question is from Faith. As a product manager and former business systems analyst, I'm super excited about this. Less pressure on me to think of everything, no endless follow-ups. There will still be follow-ups, maybe just not as many. I'm working with a business architect called Wendy Kuhn on how to apply these ideas to business structures as well. And there's a few things I'm worried about there, because people see this and sometimes they think, I'm going to build businesses or I'm going to build organizations this way. And you might have seen me tweeting about this today because it's starting to stress me out a little bit. The little n, big N relationship between software structures and the business world around them is what makes this work. And if you have a structure like an organizational structure or a business model structure, we can't really talk about the relationship between N inside and N outside anymore because there's no way to really measure that, and it can end up getting very, very messy. And so I'd be afraid that residuality theory applied to business structure might actually end up going into a tailspin and ending up back where we were reducing models. But I still haven't got that fully formulated yet. But so for the minute, my advice on business structure is just don't do it, please, until there's something that scientifically supports it. And the risk with that is that when you do this for a business structure, it's just as fun as it is with software, but it might not have the same scientific foundation. Okay, and yeah. Okay, thanks, Faith. So if you ever want to work with a product manager who understands this in DDD, hit me up. It's actually really difficult for me to hire right now, so I'll keep that in mind. So how do you inspire people to come up with stressors way outside of their normal thinking? How do you break through the unconscious bias and assumptions? And an interesting story is that on my courses and the initial courses, which were 5 years ago now, there were a lot of people who really struggled to come up with stress for their systems. And I would see senior engineers who would have a list of stressors, and they would be kind of predictable. They would be the server, the disk crashes, the network goes down. There's very, very technical things. And I spent a lot of time observing students and wondering what is it that's the blocker here? What's stopping them from being able to stress the system? And is it knowledge? Is it knowledge of business systems? Do they not understand that a merger or an acquisition has this impact on a company and therefore this impact on an architecture? Is it that they don't understand markets? Is it that they don't understand business models? And so I added a bunch of stuff to the course around those things. I created a beginner course in architecture to make sure that people coming into the advanced stuff understood the relationship between our code and our business models. And it turned out that sometimes that was some of the problem, but most of the time it was confidence. People are too scared of looking stupid, and they won't venture a stressor if they think that no one's going to agree with me, no one else has seen this, no one else has said this, there's no consensus on this, so I don't want to be the outsider that comes with this daft thing. And so what I did was half an hour for 30 full minutes before the exercise, I tell everyone in the class, look, it doesn't matter what you write down in your stressor analysis. It doesn't matter how clever you are, how much thought you put into it. Everything you write down is wrong, regardless of what you write down. It's all wrong. And the only measure of whether you've done this well is volume, not how correct it is. And you have to spend a lot of time telling them that this is the case and repeat that several times. And suddenly the number of stressors they were able to produce exploded. So there's a huge problem with I think it comes partly from our positivist educations where we have to be correct. A lot of us have mathematical and CS backgrounds. And a lot of it comes from the shame of being wrong or being embarrassed. And that's one of the things, if you're running these kind of workshops, doing these kind of things, we have to really work with making sure that people are comfortable enough to express themselves. Nothing is too stupid, nothing is too silly. And so by making it playful, we get a much broader range of stressors and we move outside of that little red circle. most people, it takes a day or so to get them moving on this. Some people find it very, very difficult to be free. Okay, thanks, Fia. And for identifying a happy path stop, you have things like event sourcing. Are there techniques like this to identify stressors easily? Stressors are insanely context dependent. So you have to, so there are techniques I teach that make stressor analysis easier. Most of them are about investigating context. So it's things like how to do industry research, how to map a market, how to understand simple things like Porter's 5 forces, how to map a business model and an operating model and understand how all of these things are linked and how they stress each other. And there are simple tools like Pestle, which allows you to look for political and economic and social things that are going to cause problems in a system. And one of the things I teach is very sloppy, simple network diagramming. So you draw some nodes and you draw some links, and every time it occurs to you that there's something out there that's connected in some way, you draw another link and another node and then stress your own understanding of it. And so using all of these architectural models to create conflict with each other is how we produce stress in our systems. Aman. Yeah. So this is a structured way of thinking, and it's very, very much the focus is on coupling. It's about making sure the end result of all this work is not about building bulletproof systems, because that wasn't the original intention. That's just a byproduct. The point of this is that we make decisions in a structured way that deals with the problems we have as architects, which we believe in, rather than a bunch of random decisions, which we then try to manage the risks of then breaking around. Yeah, so FMEA is still really important, but it's a very, 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 very technical tool. And so I use FMEA to make sure that the architectures I've actually designed, the components that I put together, that they actually work the way I think they're going to work, that I capture their failure modes. But once that happens, I've moved from the external kind of complex bubble into the ordered software system. And it's a different kind of thinking. And we're all experts at that already. Otherwise, we wouldn't be here. So that's the Dostoevsky of architecture. That sounds beautiful. Is it because I'm so miserable and depressing?
I think it's your hair.
Yeah. Okay, that's fantastic. That might get a tweet later on.
I have a last question or another question. I think we still have a couple of minutes. Incidents. Can we use incidents to think around the corner to create this matrix?
Yeah, are we still recording?
Yeah.
Okay. So incidents are concrete examples of stress. They're concrete X's that have happened in the real world. And they work in exactly the same way as a stressor, except on a different timeline. So when an incident happens, it's an X. We didn't know it was there. We didn't know it was going to happen. Otherwise, it wouldn't have happened. We'd have done something to make sure it didn't. And when that incident happens, it reveals weaknesses in our structure. It reveals weaknesses in our architecture. And when we fix it, then we are actually creating a new residue, and that residue will support a number of attractors, and there'll be a bunch of other X's that this fixes as well. And so one of the ways you could choose to do this kind of work is to build something, put it into production, let it fall over, learn from the incident, change the architecture, put it back in production, and let that happen over a number of years. And that will work if you get exposed to enough stress during that time, which you probably will. That's an incredibly expensive and dangerous way to do things. And as an architect, it's excruciatingly painful to constantly produce architectures that are not fit for purpose, that fall down, that have to be rebuilt. And what I've seen happening at a bunch of customers over the 25 years I've been working is that architects sometimes get away with doing a really, really bad job. We produce rubbish architecture sometimes. Because we don't explore any of these things. And we deliver them to operations. And we deploy them, and then we run away as fast as we can to our next project. And operations then have no other choice but to learn from incidents, because there's no other source of information. And essentially what's happening is, as architects, the architect is abstaining from their duty of producing a structure that can survive more than what they've been told about. And they're handing that over to operations, and operations will learn from incidents, but they're rescuing bad architecture. And if you have a situation where the learning from incidents is constantly shaping the architecture of your system, then you have a very, very poor architecture. And so my aim with this work is to make things a little bit less dangerous for operations. And yes, they will still learn from incidents. There will always be incidents, especially on the technical level, that we can't catch or prepare for. But hopefully we'll build architectures where the structure doesn't need to be ripped apart as much. And a very, very common pattern in that is that we deliver architectures that are set, and operations can't do anything about it, and they have to do workarounds. They have to introduce things to the architecture, but the component boundaries are already set. They have to live with the bad architecture that's been done, and that's not optimal for the organization. And I know a number of organizations where the architects have trained operations to do architecture for them. So we build something functional, and the non-functional is solved by operations. And sometimes if you have a startup where the most important thing isn't quality, isn't architecture, but time to market, we need to get this product out there, then you build something quickly and you throw it into production, and you get it to work. And because you're a startup, you're new, you're doing something different, it's the first time anyone's ever done this, no one knows how the business model works, and then learning from incidents and getting to market is the only combination of ideas that can actually work. And that's fair enough. And sometimes we'll have to roll with that. Sometimes that's the way it is. But for the majority of large enterprises, for my customers, you don't need to take those kind of risks. And so learning from incidents is fine. But as soon as someone says that, I want to make sure that the architects and the projects or in the initiatives are up to scratch, because it can be an excuse for bad architecture.
But I didn't mean just learning, just taking the incident and fixing them, but taking an idea and creating these dependencies, observing, okay, it's always the same incident happening, and which parts are coupled.
Yeah.
So applying this matrix to understand deeper where is the coupling.
Yeah.
I think there it can be used instantly.
Yeah. Yeah, and every time you have an incident, you've got to go back to your residues, you've got to go back to your matrices, and you've got to say, we've missed something. Where's the ripple? Because this changes K.
Yeah.
All of a sudden. Okay.
So maybe a last question. If there are any. You had some information about Dostoevsky. No more questions.
We have one that's come in here from Ricardo.
Oh, yes.
Sometimes business don't know up from down. How is the residuality approach impacted by this? Residuality, Ricardo, assumes that the business doesn't know what's happening. They are just as lost as everybody else. They don't know what the future holds, but they're trapped in a kind of psychological prison called the dominant discourse, which I recommend that everyone, if you're interested in these ideas, read the work of Ralph Stacey. It's a British researcher who talked about how business people are trapped in a kind of psychological prison where they believe they have to be able to predict and control and understand things in order to be confident. And that's really not the case. So residuality assumes from the get-go that everything they say is wrong. And that's why we stress things. Even everything they tell us about the business model, about processes, about cash flows, about customer behavior, it all has to be stressed and tested and say how if they're wrong, what do the residues look like? And a few more that's come in there. So yeah, some positive stuff, which is good to see. So just I think as a final point, these ideas are, I've seen, I used to think, I'm really negative and miserable, and and that seems to work well in architecture, and maybe the way to improve architecture is to make everybody negative and miserable like me. And then I've gone out and I've given these talks, and people keep saying to me, this is so inspiring, and that's a real disconnect for me. How can you get inspired by misery? But there we go. So one of the things to think about, though, is that these ideas are kind of radical. They're very, very new. And there are a lot of people, especially on Twitter, who get upset. And there are people, and that's a function of new ideas. You are going to upset people. So when you're talking about this, or you're talking about this to other people, don't give it both barrels or hallelujah. It has to be introduced kind of slowly. Because some of it is for some people, not the kind of people who give up their Tuesday night to listen to a webinar about news theories and software, but other people in our business environment who might find it absolutely terrifying to throw all of these old ideas away and start talking about lizards is a step too far for most people. So be gentle with them. And yes, stress and conflict is always the key to actually finding good things. And that's one of the things I think that people find difficult as well, especially in certain parts of Northern Europe where we like consensus and we don't like conflict. To have an architectural methodology that insists that we create conflict because it gives better results and because it's more fun is kind of foreign to those cultures, and has to be introduced sort of carefully. And I find the best way to introduce these ideas is to introduce them to groups and let the groups then figure out how to use them for themselves and see how efficient that actually is.
Could I just drop in one more question there?
Yeah.
So I guess from a point of view of introducing this to teams who probably may not have either heard of it or may not have realized the value of it, would it be then an idea to say, okay, well, maybe we probably don't have to think about NKP analysis or stressors, because this could be quite sort of heavy, almost mathematically type words. Let's just start by looking at, well, what I would call failure modes, but in a little bit more structured manner, and see how these systems could behave if one of these things were to happen. Would that be kind of a sort of a gently introducing them to this concept of thinking in failure mode terms?
Yeah, absolutely. And I think for a lot of my customers, for a lot of the business stakeholders of my customers, this is how they see it. They just hear questions from me, and they don't see it as a stressor analysis or anything radical. They just see it as someone asking them questions about how the business works, maybe with a bit of a negative slant. And it's like boiling a frog. If you throw it straight into the boiling water, it'll jump out. But if you gently heat it up before they know what they're talking in mathematical terms about networks and K and to slowly introduce it. But absolutely, and any one of the things that I've talked about, the stressor analysis, the suspension of belief and probability, the use of matrices, any one of those things will give a positive result in a project. You don't have to use all of this together. There's no purity to using these ideas. You can take little fractions of this and add it to your already defined architectural process and see how it works and test it. There's absolutely no impetus or need to take all of these ideas all at once into your projects. That's probably overwhelming for most people. It takes a little bit of testing and reading and playing to understand how each one of these things works, and maybe a little bit longer time to understand how each of them interact with each other. And so one of the things that I'm working on at the minute is the sort of the idea that maybe these ideas are better taught over the course of a university term than in one solid block, so that people have time to digest them, work with them, put them all together. But and so yeah, I might start teaching the ideas in that way across a longer period of time, to give people time to digest the first step before they move on to the second, and then time to put those two things together and understand the interplay with each other as well.
Awesome.
Yeah, the ideas actually go very, very deep. What I'm actually talking about is essentially post-structuralism applied to architecture. So every time we think we've got to the bottom of this, there's another layer of fun to be had beyond that. And yeah, you can't give that to everyone all at the same time.
Well, thank you very much, Barry. It's there's lots of good food for thought, but also I've got lots more questions perhaps to be thinking about.
Yeah.
But I like the
Thanks.
ideas here.
Yeah, thanks for all the questions and engagement. It's always cool to have someone.
Thank you very much. I think this is a great last sentence. Let's close the same. Thank you everyone for being here. And thank you, Barry, for this mind-blowing talk. So.
Cheers. Thanks for having me. Yeah.
Thank you.
Yeah. Good luck out there. Cheers.